Let me give you another example. I do not know if we talked about this, but this is, we talked about something called functional groups. Okay, so the functional group that I want you to know, and there's several, and you'll learn a lot about this in organic chemistry, are the alcohols. Okay, so that one was ethanol, but ethanol is not the only alcohol. All right, so there's methanol, ethanol, propanol, butanol, so on and so forth. Okay, all alcohols are going to have the OH group. OH group. Okay, what is the OH group? Okay, the OH group is called hydroxyl. Okay, so all of these are going to have OH at the end, all of the alcohols. Okay, so you can use this on the exam. I guess if you take organic, you'll definitely want to memorize this, but I'll have this out and I'll give this at the end of class. It's a handout of all the important functional groups, at least for this class, and definitely you'll have to memorize these for organic chemistry, but some of you are not taking that, and you do not have to memorize this for my class, but you can use this for the exam. Something I made of all the different, at least in my mind, all the important functional groups. Okay, so one of them are the alcohols. Okay, here's another one right here. These are the ethers. Okay, they have the oxygen at the end. Okay, so here we have an ether. This is called dimethyl ether. Excuse me. Okay, the oxygen is right in the middle. Okay, this is called dimethyl ether. Okay, this is called a methyl group. So we have CH3CO, CH3 dimethyl ether. We have ethanol. What I want to convince you is that these are just different arrangements of the atoms, right? So I can take this ether, that red is the oxygen, I can move things around. Okay, remember the worst magic trick ever? Okay, I'm going to take this, move things around, and make this into the alcohol. Okay, specifically ethanol. Just moving things around here. I'm not adding any atoms. I'm not removing any atoms. And I get ethanol. Okay? Another functional group. Okay? So they're both the same thing, just they shuffled the atoms around, a different arrangement of the atoms. So both have 2 carbons, both have 6 hydrogens, both have 1 oxygen. Okay, but check this out. One of them has a boiling point of 78.4 degrees. The other one has a boiling point of minus 24 degrees C. Okay, so why is that? Okay, it's the same reason why ethanol and water come together. Okay, whereas oil and water do not come together. All right, so all of this comes down to IMF, intermolecular forces. Right, so there's about 4 or 5 intermolecular forces that I want to teach you in today's class. So let's go ahead and do that. I'm going to move to the next page. Okay. Any questions or comments? Feel free to interrupt within reason. Okay, I don't want to lose my flow. Yes. All right, so we're going to focus here on liquid-liquid interactions. Okay, liquid-liquid intermolecular forces. Okay, we can have solid liquid IMF, we could have liquid gas IMF, we can have all different types of IMFs, but we will focus on liquid and liquid. Okay, the different phases. All right. So let's go ahead and talk about our IMFs, okay? The first one I want to talk to you guys about is called Ionic. Okay, Ionic. Okay, this is the strongest IMF. Okay, do you guys remember from Chem 1 what an ionic compound is? Okay, what is an ionic compound?
It has one metal and one non-metal.
One metal with one non-metal. What happens during an ionic bond, or when you form an ionic bond? That's correct. You're very correct. It's a metal and non-metal, but what's happening? What's getting exchanged? Electrons, okay? The key word here is the full electron, not partial, not, not half-seas, okay? I have a little bit of, no, okay? It's full. I give you 2 electrons, you take those 2 electrons. I give you 1 electron, you take that 1 electron. So this is a full electron transfer. Okay, I give you 1, you take it. That's it. Okay, that is a full charge of the electron gets transferred. Okay, that complete total electron is going to get exchanged. I give it up, my partner takes it. We form an ionic bond. This is very, very strong. Okay, what's an example of an ionic compound? Okay, the very, very classic, the very stereotypical example of an ionic compound is sodium chloride. Remember sodium chloride? Table salt. Okay, sodium gives up an electron, becomes positive. Who takes that electron? Okay, Cl, chlorine, takes that electron. By virtue of it taking that 1 electron, it becomes negative. And then we do what we call a switcheroo. And then you get sodium chloride. Okay, this is a very, very strong intermolecular force. Why? Because it's a full transfer of an electron. This is not sharing. Okay, it is literally giving and taking. Okay, and if you ever get the chance in a textbook or anywhere under a microscope, if you look at sodium chloride crystals, okay, they look very organized. Okay, they look like a lattice. What is a lattice? There's no wrong answer. So what do you guys think a lattice is?
It's like the cross, like wooden things you see like in gardens and all that, where plants climb up. Something I can think of a lattice.
No, that's a good one. Yeah, I think I'll steal that. Go ahead.
It kind of looks like a grid.
A grid. Okay, yeah. So these would be atoms. Very good. Nice job, Amanda. Nice one too. Okay, so it's very organized. They have a lattice-like structure. So it's very hard to disrupt that. It's very hard to break that apart because, again, at a molecular, at the atomic level, there's an electron that's being exchanged. Or sometimes, in some cases, it's 1 or 2 or 3 electrons that are being exchanged. Okay, so this gives it, or this imparts upon the ionic compound, a lot of stability. It's very, very stable. Okay, so if you look at sodium chloride under the microscope, it looks like a lattice. Okay, so it's very hard to break apart. Okay, it's a very strong IMF. All right. So any questions on this? Okay, and what is an ionic compound? I think you mentioned this, Bailey. A what and what? Metal with non-metal. Okay, so this is the strongest intermolecular force. All right, the next two. Okay, the next two. All right, the next two belong to the same category. Okay, these two, so I'm going to call this 1, 2, 3. Okay, these 2 and 3 belong to the same category. Okay, and that's called polar. Have you heard of polar molecules? Yes? Okay, I heard it, yes. Good. polar molecules. So unlike an ionic compound, which is the strongest IMF, it's strong because it's a full, Maria, I give you 2 electrons, you take it, that's a really strong bond. This is not a full charge exchange. This is partial charge, partial. Okay? So while number 1 is a strong attraction, it's the strongest, number 2 and 3, IMFs, intermolecular forces, this is a partial charge interaction. Not full, but partial. Okay, so of the polar, we have a special type of polar, and that's called hydrogen bonding or hydrogen bond. Okay, for a hydrogen bond, I just want you to know these 3 things. Let me give you the nitty-gritty before I expand on this. Okay, the dirty trick for a hydrogen bond, not dirty, but the trick is this. Okay, you're going to look for 3 things. Okay, you're going to look for OH, NH, and F. OH, NH, and F.
So when you find it was OH, F, and N?
NH.
NH
On a molecule, you should think hydrogen bonding. Okay, OH, NH, and F. This is what you should think of. You should think of hydrogen bonding. Okay, you see OH anywhere in the molecule, NH anywhere in the molecule, F, fluorine anywhere in the molecule. I teach biochem. We really don't see F, fluorine, a lot in fluorine biochemistry, but OH and NH, yes. OH, some amino acids contain OH. That hydroxyl group. Glucose contains a lot of hydroxyl groups. Maybe you know this for biology. Proteins contain NH groups. So basically, there's a lot of hydrogen bonding that can occur in the cells, in our cells, in the macromolecules in our cells. So anyways, for this class, OH, NH, and F. And then we can consider that a very special type of polar bond, which is the hydrogen bond. All right, let's talk about water for a second here. Let's talk about water. All right, so this is a partial charge interaction. Okay, we're going to have a partial, not full, partial positive interact with a partial negative. Partial positive charge interacting with a partial negative charge. Okay, the key word here is partial, not full. So it's strong, but is it stronger than ionic? No, it's not stronger than ionic. Okay, so let me give you an example of water. Okay, so let's go to the next page here. Let's talk about water. So water is an amazing substance, I must tell you. Okay, so there are people who have dedicated their life to talking about water. There's people who have studied water. I went to a talk 2003, so almost 20 years ago, more than 20 years ago, and the keynote speaker was a chemist, and what was he talking about? Okay, he spent the whole hour talking about water. Okay, so this is an amazing substance. Okay, our bodies are 70% water, our cells are 70% water. I've asked this question: how many of you have had an MRI done, imaging? Okay, probably all the athletes have had it done. So when you have an MRI done, you're imaging water, because water has this ability to be magnetic. Okay, so the whole basis of radiology revolves around water. So let's talk about water for a second here. And also we used water as an example. Water and ethanol here. Water and oil here. So some of the properties of water it's worth noting about. So first of all, water is not linear. Okay, water is not linear. Water is bent. Okay, bent. Do you remember this from Chem 1? Okay, so the biggest misnomer, people think water is a linear molecule. Okay, it's not. Okay, this pair of electrons and that pair of electrons, the two pairs, they constrict the molecule. Okay, they bend it. Okay, they constrict it. So the structure, first of all, is very unique in that it's called bent. Okay, the second thing about water molecule is that this bond here between this hydrogen and oxygen, I want to convince you that it's not a 50-50 bond. You know a bond, right? Okay, we have a bond together, 50-50. But this is not 50-50. It's not equal. Okay, this is an unfair bond because oxygen is electronegative. Have you heard of this term, electronegative? A lot of those atoms where oxygen is located, definitely the halogens, they are electronegative, which means that this bond and this electron density is getting disproportionately pulled. This oxygen is pulling. It's like a vacuum cleaner, pulling and sucking on this electron density. Okay, so this is how we depict this. Okay, you're going to draw an arrow. Okay, give that arrow a tail. And it's pulling, and electrons are negatively charged. So this is going to be partial. Okay, this is the Latin letter delta. Partial negative. Okay, this is called delta. Well, if this is partial negative, what will that make the hydrogen? Partial positive. Okay, what about the other end? Okay, it's going to be the same thing. So this oxygen is pulling, making that partial negative. This hydrogen here, like before, will be partial positive. Okay, so two things I want to tell you. Water has a dipole moment. So if you take higher chemistry classes, I'm sure they'll talk about this term called dipole moment. One part of the molecule is partial negative. Partial. What's the other ends of the molecule? Partial what? Positive. Okay, so we call molecules with a dipole moment, we call them polar. Polar. So water, amongst its many magnificent qualities, is polar. This is a covalent bond, H, covalent bond to an O, covalent bond to an H. So it's, polar covalent, if you want to call it that. We'll call it that. And now, what will this partial positive what can it interact with? What do positives interact with? Negatives. It can interact with a negative, full negative charge. It can also interact with a partial negative. Okay, what partial negative can it interact with? Okay, I'm going to say let it interact with a partial negative of another water molecule. Can we do that? Okay, yes. So this partial positive can interact with many things, but I'm going to have it interact with the partial negative of another water molecule. How about this partial positive? Same thing, right? Yes, sir. I'm going to try to draw this right, but I'm running out of space. Okay. What do you think this partial negative can interact with? It can interact with any type of positive, but I'm going to have it interact with a partial positive of another water molecule. And this can go on and on and on and on forever and ever, okay, all across the three-dimensional space of the water molecule. Okay? So what do we have here? Okay, we have a very strong attraction. Okay, I want to bring your attention to this, okay? Okay, we have this OH, and then we have this dotted line with another O. Okay, let's look here. We have an OH, we have a dotted line with another O. Okay, look at this. We have an O forming with a dotted line, a strong attraction with this H from another water molecule. Okay. So these dotted lines are is a very attractive force. Okay, I'm mumbling my words. It's a very strong attractive force. What did we say are the three things we should look for when we're looking for a hydrogen bond? Three things. Okay, OH, NH, or F. Okay? And what we see in the water molecule is an OH hydrogen bonding to an O, an O hydrogen bonding to an H and an O. We have an O with an H hydrogen bonding to an O. What I'm trying to tell you or convey to you is that water is not only polar, not only covalent, but what else can it do? What else can it do?
Hydrogen bond with itself.
Hydrogen bond. Hydrogen bond. Okay, so water can hydrogen bond. Okay, where's the hydrogen bond coming from? Again, O, H, and O. O, HO from this molecule. Okay, we have an H, a hydrogen bond with an OH of this molecule. Okay, either whatever OH. Okay, we have an H, we have a hydrogen bond with an OH. Okay, whatever, this OH or that OH. Okay, so water can hydrogen bond. Okay, so that's the important point. It's polar, and it can hydrogen bond. Okay. So this is a very, very important type of attraction. Is it stronger than covalent? I'm sorry. Is it stronger than ionic? I made a mistake. It's not stronger than ionic, but is it strong? Yes, okay, but not stronger than ionic. Okay, so this is a very, very important intermolecular force. Okay. It's so important that they have an entire book dedicated to it. Okay, called The Hydrogen Bond. Have you seen this book? Okay. So an entire book just on the hydrogen bond. Okay, so let me show you how many pages they dedicated to the hydrogen bond. 460 pages. Okay, 460 page book on the hydrogen bond. So, yeah. Okay. So if you don't know this now, make sure you know that this is a very important intermolecular force. You can see some of the hydrogen bonds in molecules or in organic chemistry, or some of these molecules are found in our bodies. Okay. So here we have the same thing. O, hydrogen bond with an H and another O. Okay, O, H, and O. Okay, here we have HO, and this is bound to another H on that CH2. Okay. So, yeah. Hydrogen bond. If you want some good bedtime reading, you can also try this. right, so it's important. And is a hydrogen bond polar? Yes, it's polar. Okay. So let's look at another example here. Okay, let's look at dimethyl ether. Let's talk about the ethers for a second. As an example, dimethyl ether. Okay. Okay, so we'll draw this more formally. Okay, remember this is dimethyl ether. Okay. So the question for you guys is dimethyl ether polar? Yes or no? Okay, we have an oxygen here. What will the oxygen do? It'll pull. Which way? Towards itself, making this carbon partial positive. Okay, what about the other end? Same thing. Okay, so we know that it's polar. Okay, is it covalent? Okay, the answer is yes, because these are all covalent bonds, so it's kind of a moot point, but it's covalent. The question is, can it hydrogen bond? Okay, what are the three things we look at for hydrogen bonding? Correct. So can dimethyl ether, this particular ether, can it hydrogen bond? Yes or no? Okay, we have yes or no. I'm getting like mixed responses. It's not a resounding yes or it's not a resounding no. Okay, OH, okay, NH, fluorine is not there. Okay, carbon, hydrogen, and oxygen. So what do you think? Can it hydrogen bond? What do you guys think? How many of you say yes? Okay, how many of you say no? I think the no's have it. Okay, the no's are correct. This cannot hydrogen bond. There is no OH, there's no NH, or there's no F in the molecule. So this cannot hydrogen bond. Okay. So this is a partial negative, and it can interact with a partial positive with a partial positive of another dimethyl ether, but it's going to be with the partial positive of this carbon. Okay, so there's carbons nowhere to be found in a hydrogen bonding interaction. Go ahead.
So the oxygen would have to be bonding directly to the hydrogen?
Yeah. Right. There has to be an OH, yeah, or an NH.
And then for F, though, so if there's just like a single F present, it doesn't really matter what it's bonded to, as long as there's an F present, it also makes it a hydrogen bond?
There needs to be a hydrogen also somewhere. Because a hydrogen bond means a hydrogen.
Oh, but with F, that hydrogen and the F don't have to connect, correct?
They don't have to connect, yeah. As long as that other hydrogen is connected to an electronegative atom. So you can have an FHO. Yeah. The whole idea is that the hydrogen is a partial positive, and then the F being electronegative makes it partial negative. Yeah. So it's not just an H, it has to be a partial positive H. So that's a good question. All right, so does everyone see why dimethyl ether is polar covalent but cannot hydrogen bond? Okay, so we're looking at OH, NH, or F. All right, so dimethyl ether is polar. Water is polar. Okay. Water can hydrogen bond. Dimethyl ether cannot hydrogen bond. Let's go back to page 1 of our notes here. Okay, why do you think we have such a discrepancy in the boiling points of ethanol, which is an alcohol, and dimethyl ether, which is an ether? Okay, why do you think one has such a high boiling point? You need to put in a lot of energy to get this to boil, to form, get into the air, vapor. And you need practically nothing to get this into the atmosphere. Okay, why is that? Knowing what we know now about the IMFs. Go ahead.
Is it because of the oxygen? So the oxygen base?
Okay, what can ethanol do?
Hydrogen bond.
Okay, so the primary IMF for ethanol is what is it, Eric?
Hydrogen bond.
Okay, and what is the primary IMF for dimethyl ether? Which one would it be? Dipole or polar?
Yeah.
Okay, polar, very good. So which is stronger, hydrogen bond or polar? They're both polar, by the way. This is also polar. Okay, but this is just polar. This is polar and a special type of polarity called hydrogen bond. So which is stronger? Hydrogen bond is much stronger. Okay, so this is the reason why ethanol has such a higher boiling point, because it takes a lot to get it to boil. One ethanol molecule with another ethanol molecule with another ethanol molecule are all hydrogen bonded together. Okay. Why do you think water has a boiling point of 100 degrees C? Where's all that heat energy going towards? Breaking up what?
The hydrogen.
It's breaking up the hydrogen bonds. Okay, so this is a very strong intermolecular force. Okay, if I were to put something like NaCl here, sodium chloride, okay, what do you think the boiling point of sodium chloride will be? Higher or lower than ethanol? Higher or lower than dimethyl ether? What do you think it would be without looking at your phones?
Lower than ethanol.
Higher or lower than ethanol?
Lower. Lower.
Okay.
Would you be higher?
Okay, what is the primary intermolecular force for sodium chloride?
It's ion.
Ionic. Okay. So what would the boiling point be, higher or lower than these two?
A lot higher.
A lot higher. Okay. I don't know what it is, but it's a lot higher. Okay. Because ionic is the strongest intermolecular force. Okay. So this would have the highest, any ionic compound would be higher than anything that's hydrogen bonding, which in turn would be higher than anything that's just simple dipole-dipole. All right? So without looking at anything, we should be able to know which has the highest boiling point and which would have the lowest boiling point. All right, let's go back here to page 3. All right, let me just quickly go over these pictures here. All right, so this is dipole-dipole force. This also is the same thing as polar. Okay, so dipole-dipole means the molecule has a dipole moment. Okay, all of this is a partial negative with a partial positive. The key word here is partial. Partial. Okay. And then you can have, and so examples of this would be water, the dimethyl ether that we talked about before. What else is polar? Well, yeah, Okay, so those are the molecules, the ethanol, okay, the alcohols. Okay, they would have by the electronegative atoms present, okay, they would have a dipole moment. All right, let's look at ion dipole forces. All right, so ion dipole force, what is an ion? This is the full charge, okay, a full charge, sodium, okay, Cl minus chloride ion, okay, magnesium plus 2. This is the full charge interacting with a partial charge from the dipole. This is an ion dipole force. Okay, a full charge of the ion, either positive or negative, interacting with the partial charge of another molecule, either partial positive or partial negative. Okay? So let's give an example of ion dipole with something called solvation. Okay, have you heard of this term, solvation? Go ahead.
I'm sorry, I probably forgot about it, but how do you also do you like quickly remind me, like, how do we know if the charge is full or partial? Like, for some reason it went over my head and I didn't write it down.
How do you know when it's full or partial?
Yeah.
You have to draw the structure of the molecule, and if there's an electronegative atom, it's going to pull on it. But if it's an ion, it's just going to look like this.
Okay. So it's full, it has like an electron, if an electronegative atom is present, then it's going to be full. But if there's not one present, it's partial.
If there's an electronegative atom present and it's going to pull, it's going to be partial negative, making the other one partial positive. And these are just ions. Yeah, this is a partial negative charge. Okay, these are all partial. Okay, this is a fully positively charged sodium ion. This is a fully positively charged magnesium ion plus 2. This is a fully charged chloride ion minus 1. So full ion, full charge, partial charge.
Okay, partial means that's like kind of like a one-way full kind of thing. Is that what you're saying? Like there's like a kind of one-sided attraction.
So part of the molecule is partially positive, the other part is partially negative.
Oh, and then the other one is like it's fully either positive or negative.
Ion will be like just an ion, like we learned in Chem 1.
Okay.
So an ion dipole is the full positive interacting with a partial negative. Okay, so maybe this will help you understand it better. If you take NaCl, which is salt, and put it in water, okay, this is called solvation. Okay, because amongst many of the other unique properties of water, one of them is that it could solvate. In other words, this water can actually take this lattice that we were referring to before and break it apart. Okay, this is why salt dissolves in water. And you have a sodium ion interacting with the partial negative of the water. It's like a water shell or solvation shell. Okay. And then you have the chloride ion doing the same thing, interacting with the partial positives of the water molecule. Okay. A solvation shell. So that's what you see over here, okay? All the water molecules hydrate. They form a solvation shell around the full negative chloride atom and around the full positive sodium ion and the full negative chloride ion. Okay, solvation shell. This is called solvation. and that is an ion dipole force. Okay. It's not dipole, it's ion dipole. See, dipole would be two dipoles attracting. Ion dipole is an ion interacting with a dipole, positive with a negative. Example of this ion dipole is solvation, putting sodium chloride in water, putting magnesium chloride in water, putting, lithium chloride in water, sodium hydroxide in water. Water has this amazing capability to actually disrupt this lattice and put a solvation shell. Okay, the partial negative of this polar compound interacts with the full positive all around it. The partial positive of this polar water molecule, partial positive, interacts with the full negative of this chloride ion. Okay, so that's ion dipole, not to be confused with dipole. It's kind of the same thing, but this one is a full ion. An ion is a full positive charge. An ion is a full negative charge. All right? So that is another IMF. Okay, the final IMF that I want to talk to you guys about, and then maybe we'll do some practice problems, and then maybe we'll call it a day. Maybe we'll stop at page 8. Page 8 is a good stopping point. All right, dispersion forces. Okay, so I have here a handout for you guys. You can take it before you leave. Dispersion forces are very, very weak. This is what I want you to know about dispersion forces. Very weak. Okay, they're very temporary and fleeting. They involve circulating electron clouds. You know, electron clouds move around. Okay. And by virtue of them being very, very weak, and they're temporary and fleeting, and they're based upon the electron clouds, then temporarily move around the whole molecule. It's a very weak IMF. And what do we associate dispersion forces with? Sometimes this is called London dispersion forces. Okay, we associate them with nonpolar molecules. Not polar. What's the opposite of polar? The opposite of polar is nonpolar. Okay, what are nonpolar molecules? Okay, they have no dipole moment. Okay, no partial positive, no partial negative. They are just neutral as neutral can be. Okay, they have no dipole moment. The best example of dispersion forces, here's another functional group, are the alkanes. Okay, let's talk about the alkanes for a second. Come on. All right, the alkanes. How many of you have heard the term alkanes before? Okay, nobody has heard of the alkanes, but I bet you've heard of methane. Have you heard of methane? Okay, that's one carbon. Okay, what's two carbon? Ethane. Okay, what's three carbon? fuel for the barbecue. Okay, I think, don't they use it in gas? I'm not sure. Propane. What's 4 carbons? Butane. I think this is the one that's in cigarette smoke, cigarette lighters. I'm not sure. Anyways, butane. Not butanol, but butane. What's 5 carbons? Pentane. Okay, what's 6 carbons? Hexane. 1, 2, 3, 4, 5, 6. Okay, what's 7 carbons? Okay, heptane. Okay, what's 8 carbons? Octane. Okay. What is 9 carbons? Okay, what's 10 carbons? Decane. So we have another functional group. This is not the alcohols. Okay? This is not methanol, ethanol, propanol, butanol, pentanol. These are the alkanes. And what do all the alkanes end with? Okay, ane. So what do you know about the structure of these? Okay, you remember Lewis structures from Chem 1? Okay, what do you think about the structure of methane? Okay, what do you guys think? Is it polar or non-polar?
No.
Okay, it's 100% non-polar. So what's the main IMF for dispersion forces? Is there a net partial positive charge here? No. Is there? Carbon does not pull. Hydrogen is very weak. It does not pull. Nobody pulls here. So what do you think what do you? I'm trying to say, is there any partial positive here? No. Is there any partial negative here? No. Is there any positive charge here? No. Is there any negative charge here? No. Okay, what charge is there in here? Nothing. Okay, what's the main intermolecular force? Nothing. But actually it is something. It's the very weak dispersion forces. Okay. London dispersion forces. Okay. So you can read the definition of dispersion forces here. I got this from the textbook. You can also read the discussion in your OpenStax ebook. But basically, if you have a molecule, there's electron clouds circulating. And as the this is very weak. Okay, I have to tell, this is very, very weak. As the electron clouds circulate, electrons are a little bit negatively charged. As the electron clouds circulate, the negatively charged cloud, as they circulate, can temporarily induce a molecule to orient to its temporarily positive charged end. Okay, so if this electron cloud circulates, it's a little bit temporarily negative here, and that will make this molecule temporarily positive here. Temporarily negative here will attract a temporarily positive dipole here. Okay, the electron clouds circulate. But this is very weak, and that's the only thing I want you to know. It's super weak. Okay, super weak, and it's almost fleeting. You know what fleeting means? It just comes and goes, because, electrons move around the molecule. So this just comes and goes. By virtue of it just coming and going, we say dispersion forces are very, very weak. Okay, it's a very weak intermolecular force. And I want you to associate the dispersion forces with all the alkanes. Okay, which you'll see here. I'll give you a copy when we end class. All of these alkanes. Okay, and this is how they look like. Okay. Sometimes we also call these hydrocarbons. And this is what you'll learn in organic chemistry, so you do not have to worry about this, the different way of drawing the structures. Right, so you can bring this to the exam, it's not a problem. But what's the main IMF for the alkanes? Dispersion, okay. London dispersion forces or dispersion? Very temporary, very, very weak. What would be the main IMF for CCl4? Carbon tetrachloride is the name of this molecule. Carbon tetrachloride, CCl4. Okay, the first thing you would do is draw the structure. Carbon loves 4. Okay, chlorine is a halogen. Which means it pulls, just like the oxygen and all those in that area. So what do you guys think? What's the main IMF here? Polar or non-polar? Go ahead. Non-polar? But these chlorines are very electronegative. Okay, why do you call it non-polar? Why do you call it non-polar? Very good, Maria. They cancel each other out. So even though this has electronegative chlorines, this chlorine pull cancels that chlorine pull. Okay? And the chlorine on the right-hand side cancels out what? The left side. Okay, so when all these vectors cancel out each other, even though you have electronegative atoms, this is still nonpolar. And if it's still nonpolar, what is the main IMF for this? The main IMF is dispersion because it's nonpolar.
So with non-polar stuff, the main stuff we have to look at for the IMF is just the older dispersion.
Okay, if it's nonpolar, then dispersion. Okay, how do you know if a molecule is polar or nonpolar? Okay, you generally look for symmetry. Okay, this molecule has symmetry. You know, this Cl counterbalances that Cl counterbalances that Cl. So even though there's electronegative chlorines and they pull, there's symmetry, and the symmetry tends to cancel out all those pulls. Okay, so nonpolar, look for symmetry. If it's asymmetric, okay, like a water molecule or an ethanol molecule, then it's polar and it will have a dipole moment. All right, let's go back to page 1 just for a second here. Just for 30 seconds. So the highest boiling point would be something like sodium chloride. Ethanol, which is an alcohol, has the OH group, which makes it hydrogen bond, which gives it a very high boiling point because all that heat energy is going to disrupt those hydrogen bonds. This dimethyl ether is polar, and even though it is polar, it cannot hydrogen bond, so the attractions are strong but not very strong because minus 24 degrees C is a very low temperature to get this molecule to boil, even though it's polar. What if I add to this list ethane? Or actually propane, since we can get propane from the fuel store, from the fuel company. And we can get propane from our chemical companies here too. Where would you rank propane here? Okay, without looking at your phone. Where would propane be? Highest or lowest? Or middle? Mid. You know, people are saying mid. I did not know that this generation, they're saying mid means like bad. Someone said, "Oh, you're so mid," or "That's mid." Like, what is this word? I realized they're saying like you're like an idiot.
With mid usually kind of means like, oh, you're average, but it's a negative connotation, basically.
Yeah. Oh, you're so mid. Like, what is this
As in,
people talking about?
as in you
Mid.
aren't going
That must
above
be
and
so
beyond.
old.
It's like you aren't going above and beyond for anything.
Hmm?
Think of it as in like saying like, oh, like, you're about average, but you're not going above and beyond, basically. Yeah, you're just boring.
So as a professor in your evals, you can say, "Oh, he's so mid." Like, what does this mid means? Anyways, where's propane? Is it highest amongst these four, lowest amongst these four, or is it mid? Highest or lowest? It's going to be the lowest. Lowest. Okay, why is it the lowest? Even lower than this one here. Okay, why is it the lowest? Because dispersion, forces, and nonpolar. Very good. Okay, so it's going to be the lowest. Mid. I can't even. I don't know this. I want to go back to when I was a kid. The 90s or the 80s. All right, let's finish this up here. All right. All right, let's go back to the hydrogen bond here for a second. All right, just as a review here, we're talking about ionic. That's the strongest. What's the next strongest? Hydrogen bonding. Okay, what's next? Very good. Dipole-dipole or polar. This is also dipole-dipole, but you're right. And what's the weakest? Dispersion. Okay, which of these four, which ones are polar? Okay, which one are you going to look for a nonpolar? Okay, in terms of strongest. Okay, weakest. In terms of boiling point, highest. Ionic, right? You agree? And lowest? Okay, what about these guys? Which would be higher? Hydrogen bonding or dipole-dipole? That's the key. And what do we look for hydrogen bonding? Look for OH or NH or F anywhere in the molecule. Okay, and that gives it a strong attraction that makes it polar but stronger than ordinary dipole-dipole. All right, let's just go over this because this hydrogen bond is something you'll see a lot, especially if you take, even the biology majors will see this, so it's worth going over this one more time. These are hydrogen bonds. Okay, these are hydrogen bonds. So water and water. Okay, so just follow along with me. Okay, O, hydrogen bond HO. All right, the NH3, that's called ammonia. Have you heard of ammonia? Okay, so ammonia is NH3, and there's some NHs in there, so it can hydrogen bond to itself. Okay, just watch with me. Okay, you have N, hydrogen bond HN. All right, water and ammonia. O, hydrogen bond HN. Okay, so maybe you can see a trend here. Ammonia and water, okay, this and this. They flip it. N, hydrogen bond HO. Okay, I just want you to follow with me. Okay, hydrofluoric acid HF, hydrogen bond HN. Ammonia and HF, okay, the other way around, N, hydrogen bond HF. Okay, so it's two molecules. There's a hydrogen, and that hydrogen is partial positive because that hydrogen is attached to a electronegative atom. Okay. So this is what you kind of want to see when you're looking for a hydrogen bond. Okay, the OH, NH, and F. All right, this will be our last page for page 7, unless we want to continue on. We'll see. I just want to go over this with you here. All right, why do you think tetramethyl ammonium chloride has such a high boiling point? Why is it? Okay, the answer is right here, ionics. See, you have a full positive with a full negative. Okay, why is N-butylamine have a boiling point of 77 degrees? So you do not need to know this, by the way. You don't need to know this, but each of these points represents a carbon. Okay, each of those points represents a carbon. So that represents a carbon, so that's a carbon fully saturated with hydrogen. That point represents a carbon fully saturated with hydrogen. And you don't, I will not test you on this, you do not need to know this. That's a carbon fully saturated with hydrogen, and that edge or that point is a carbon fully saturated with hydrogen. So here we have a carbon, okay, and that nitrogen is being pulled, but we have an NH here, so that gives it hydrogen bonding. Here we just have an N, but that's a carbon, that's a carbon, that's a carbon, that's a carbon. So the nitrogen pulls, making it partial negative. So this is just dipole-dipole. Right. So same thing along this corner here, or this section, the carboxylic acid functional group. Okay, here's the amine functional group. Again, ionic compounds, very large boiling point. Why is that? A full positive with a full negative. Okay. Why does butyric acid have a pretty high boiling point of 163 degrees C? What's causing that? The hydrogen bonding is causing that. Where's the hydrogen bonding coming from? Okay, the OH. Why is this just dipole-dipole? Okay, there's no OH, there's no NH, there's no F. Again, this point is a carbon, which you do not need to know. That's a carbon bonded to an O double bond, that's an oxygen, that's a carbon with a bunch of hydrogens attached. Right? So that's how it works. The highest boiling point is ionic. The higher boiling point is hydrogen bonding. This is polar, and it has a high boiling point, but it cannot hydrogen bond, so it's kind of lower. Do you see what I'm trying to get at here? Alright, so that's the scheme here. Alright, let's see if we can quickly finish these practice problems. This should take no more than a couple of minutes, and I think, when do we leave? I lost track of time. Okay, so let's just go over this really quickly. And then I think we're at good pace to start the next part next week. All right, just a couple of more minutes here. Okay, thanks for your stamina and perseverance. Okay, which of the following species are capable of hydrogen bonding amongst themselves? Hydrogen bonding with itself. Okay, can H2S hydrogen bond with itself? Hydrogen sulfide? No, there's no OH, there's no NH, there's no F. Okay, can benzene hydrogen bond to itself? Benzene? Yes or no? I don't know if you know benzene. Can benzene hydrogen bond? Benzene is a ring. Okay. Can it hydrogen bond? Okay, OH, NH, and F. Okay, what's the main IMF for benzene? C6H6. Okay, what's the main IMF? Dispersion. Dispersion is the main IMF for this, not hydrogen bonding. What's the main IMF for H2S? Sulfur is electronegative. Dipole, dipole. Okay. And what about this? Can it hydrogen bond to itself? Yes. Okay. Why can it hydrogen bond to itself?
As an OH.
Because of the OH. Okay. What type of functional group is this called? What's the name of this functional group? Functional group, not the name of the molecule. Alcohol. Okay, alcohol. What's the name of this specific alcohol? What's the name of this specific alcohol? Methanol. Okay, methanol. All right, how about hydrogen bonding with water? All right. Can dimethyl ether hydrogen bond with water? Yes or no? What do you guys think? You think it can hydrogen bond? Okay, yes. Okay. OHO. So with water, it can't hydrogen bond. Okay. You can see that hydrogen bonding interaction here. Okay. What about B, CH4? What do you guys think? Okay, no. The answer is no. Okay, what's the main IMF for CH4? Dispersion. Okay, what's the name of the functional group? Alkanes. What's the name of this specific alkane? Methane. Okay, so it cannot hydrogen bond. This can, part A. What about part C, F2? This is a trick question. F2, can it hydrogen bond to water? Okay, draw the Lewis structure. What does the Lewis structure tell you? So drawing the Lewis structure of F2, what does that tell you? F2 is it polar or nonpolar? Nonpolar. So if it's a nonpolar molecule with no partial positive, no partial negative, you see the partial negatives cancel out with each other. Can fluorine hydrogen bond with water? Very good. The answer is no. So this is no. Okay, even though there's a fluorine there, it cannot, because the whole molecule is nonpolar. This fluorine cancels out. That pole and the other fluorine it's covalently attached to cancels out the other pole. All right, last two here. How about this? HCOOH. This is called formic acid. It's a carboxylic acid. That's not something you need to know, but the answer is yes. This can hydrogen bond with water. Okay. And finally, part E. Can part E, sodium ion, hydrogen bond with water? Can sodium ion hydrogen bond with water? Yes or no? OH, NH, or F? No. Okay, this cannot hydrogen bond with water. What would the sodium ion and water be if they were to interact? Okay, it would be ion dipole. Okay, but definitely not hydrogen bonding.